Let's jump right in and build our first model. Our first exercise is going to be to build a one-mass oscillator, and we want to compute the transient response over 10 seconds. Within that transient response, we will analyze the spring and damper forces and the displacement and the velocity of the mass. We can see here on the right-hand side the schematic diagram that we'll be building in SimulationX. First, if you still have this hydraulic cylinder model open, we can close that by right-clicking on the tab and choosing Close Model. No need to save it. Also, if you ran a simulation, you might have information here in the output bar, and you can get rid of that by right-clicking in the output bar and deleting that so that we have a clean slate. I still have a model here open, a blank one, so I'm going to start first by expanding this mechanics library here. You can see there are different types of mechanics. We're going to start with translational mechanics, and I'm going to need various elements for building this model. I'm going to need a mass. I'm going to need a spring, and I'm going to need a damper. Now there's two ways we could model the ground. Either we use a preset. I'm going to do that just to be formal. Or you can leave these connections open. Any 1D or mechanical connection that's not connected is assumed to be connected to the ground. Now it makes no difference whether we build our model facing to the right or facing upwards. That does not affect whether gravity is considered in this model. To show you, however, how to rearrange the elements, I am going to rotate them and build them just like in the schematic diagram. So if you click on an element, sometimes twice, you will get a bar here where you can then rotate the element the way you would like to have it. So I'm going to put my preset down here. I'm going to take the spring, put that just beside. Likewise, my damper, I will rotate and put it beside the spring. And finally, the mass, I will put above here. So just make some final alignments. And now the next thing is to connect them. So if you hover over a connector, you will see it turn red, and then dragging it to another connector will create a connection. Now in this case, we have a connection here. We can either go down here, but you'll see that it's slightly different. It connects it to the connector. Instead, I want to create a node right there in that connection so that we have a nice looking connection here. And finally, we're going to draw those connections up to our mass as well. In the case you have something like this, you can always click on your connection and then rearrange it just like that. Now you may notice that the mass has two connectors on it. That's just for graphical purposes. In fact, the mass has a single connector. These are both basically the same thing. It just enables you to build the model easier and more intuitive way, continuing from there. So now that we have our model structure built, the next task is to parameterize it. So to do that, I'm going to go and double click on my spring. And that will open up a parameter dialog box here, and I can see the stiffness parameter K, which is 10 to the 5 newtons per meter. In Modelica, the shortcut for that is 10E5. That's equivalent to writing 10 to the 5th. Now I'm going to double click on my damper, and my damping constant is 150 newton seconds per meter according to that schematic. Finally, my mass is 100 kilograms. So double click on there, 100 kilograms. And the preset I don't need to adjust. You'll notice one other thing in the assignment is to analyze it over 10 seconds. So a simple way is on the Start tab here, simply to put in 10. If you want to have additional solver options, you can open the simulation properties here, where you can set all sorts of different options that we'll get into later. Next, I want to be able to see the result variable. So to do that, I'm going to select all of those elements, and I need to tell the software to record all of those results. So I'm going to right click here simply say all protocols or selection on. This is going to turn on all the result variables in those elements. And I can verify it if I want to by going into the mass. For instance, you'll see there's not only a parameters tab, but also a results tab. And I see that for all of these result variables, they all have green check marks beside them, meaning that they will be recorded and I'll be able to plot them in the result windows after the simulation. I'm going to simulate now, even though the results are probably not going to be as expected. Press the simulate. You can see it's now finished. I can then plot results in various ways. Typically, I right-click on an element and use this menu to choose the results I want to see, but you can also, from this results tab, just drag out various results. So for instance, I can click on this check mark and just drag it into the diagram view, and that will plot a result variable. This is what I meant. Results probably not as expected, and that is because everything is still static. And this is an important point about SimulationX. SimulationX is a dynamic equation-based modeling software. And that means we're calculating differential equations that represent the physics of particular systems. And this system is still at rest. To get our oscillator to actually oscillate, we do need to excite it in some way. And to do that, you may have noticed when you were setting the mass that there's also these initial values. So we need to give it either an initial displacement or an initial velocity. And I'm simply going to drag this out 1 centimeter. That'll give us an initial displacement and also a sort of an initial tension on the spring. And now when I resimulate, I'm getting values that, we can see the dynamics of the system there. That was using the magnifying class. If you use the magnifying class, double-clicking on the result window just brings you back to the full screen. So the task says to model the spring and damper forces and displacement and velocity of the mass. So I'll leave this here as displacement of the mass. Let's go back to our spring and damper forces. So I'm going to use now right-click, transient results. I'll use the internal force on the spring, popping up on my other window here. And you can drag and drop these windows wherever you'd like. So I'm actually going to drag this to the left of that mass result. Just put our spring force right there. And our damper force, internal force here on the damper. Put that in the same window as my spring force. All right. And now we've got our displacement here. Let's take a look at the velocity as well. Now you can see because these two results had the same unit, it's combined them on the same axes. Now when I go to grab the velocity here of our mass, because it has a different unit, I can still put it together with the displacement, but it's going to have a separate axis for that. And I can sort of switch back and forth to see those different results. If we zoom in, we might get a bit of a better view. Yeah, I'm going to have to take quite a close look here to see those differences. All right. So one more thing to wrap up this lesson. Let's do one thing. Let's modify a parameter. So I'm going to use this freeze button right here. I'm going to freeze this result. You can see those ones freeze. Likewise here, I'm going to freeze these ones. You can see the frozen results with the simulation run behind them. And then I'm going to go into the damper and I'm actually going to increase that damping coefficient 10 times so that it's now 100 and 1500 Newton seconds per meter. And just clicking in the diagram view will close that parameter dialog again. I can now reset the simulation and run it one more time, and we can see the difference. Now there's a lot of information in here, and so I'm going to pull a couple out. I'm going to put the old damper force. Let's put it in a new window, and we'll compare that to the current damper force. So again, the red is now our previous damp force, our green is the new simulation. And if we do the same thing with the displacement, I'm going to pull the old value out here into a new window and the new one into the same window. We can see how much quicker the mass loses its oscillations due to that higher damping coefficient.